And okay, there it is. Now the only change is this jumper came from this position a bit down, and that's pretty much it. So there is a wire schematic that I found on the internet. It does not necessarily mean it's 100% true, so this is why I'm approaching carefully with this. And I'll start again with 0 volts, making sure everything is set correctly. Okay, now let's see what's gonna happen. Slowly increasing voltage. 1 volt. It's a bit better. 2.2, but we are like 20 volts higher than in previous setting. Let's move to 240 approximately, and yep, that's much better. 4 volts, and we are at 200. It says like 220, but somewhere over here is probably 240. I'll measure that voltage later as well. That's much better. That is now much better. So yeah, we're gonna extend life of our tubes with this simple change on the radio itself. It's gonna give much better voltage, and that stands as well for DC voltage. So I'll just measure exactly 240 volts here, which is what I get in my power network nowadays. It used to be 220, but now the standard is 240. So I'll measure 240 here. As a matter of fact, I can do that immediately. And switching to higher voltage. Let's see what it's gonna say here. Okay. Yeah, this is over here. There it is. It's 240. Okay, but 20 volts. This is 240. 241. That's more or less the same. Plug in the radio again. And measuring voltage for the heating. Now look at that. 4.01. Actually, exactly 4 volts. That is just wonderful with this simple setting. So yeah, we're good. Moving forward, we will add tubes and we'll see what's going on with the DC voltage. Yeah, but before that, I'll do a couple of other measurements and we can basically pretty soon turn on this radio and see what's going on and if we are going to receive any station. At this moment I have focused on these two electrolytic capacitors, both 16 microfarads, and on schematic it's this one over here and this one over here. Those are from 16 microfarads. It could look like it's those two, but they're actually not. This one is connected with the chassis and the positive pole, and the other one is connected here to the coil, and there is a set of these resistors here and the potentiometer which is splitting those two capacitors. So C1, that capacitor, is this one over here. It's connected directly to the chassis with its negative pole, and positive is here going down to the transformer itself. When you take a look at the wiring, it's this wire, I think, over here. And when I check the connection between the chassis and between this capacitor, this is it, okay. And when I check this one, it's not connected with the chassis, and that is exactly what schematic is saying to me. But there is another issue here. When I measure resistance between this pin, which obviously should be connected with the traces of capacitor, there is no any resistance, as you can hear and see. So that is almost impossible, because the chassis of this capacitor is very tightly connected with this ring here, which there goes further to the coil. This is the coil that you saw on schematic. But there is another clue which might explain why that happened. As you can see, there was some sort of leakage here. Goes from this bolt, and there is another here, and there are traces of strong oxidation here, probably from the electrolytic fluid within this capacitor. So I think that this capacitor had leakage, and this is why we can see all of this, and that probably created an insulation layer between this ring and the capacitor itself. So just to make sure that this happened, what I'm going to do now, I will remove this wire, and I'll remove wire from the positive pole of electrolytic capacitor, and I'll try to remove the capacitor itself to see what's going on here. And just to make sure that I will replace it with a new one the correct way. So now I'm playing with this capacitor, replacing it, and this capacitor over here. So let's see what's going on there. And as I thought, when I disassemble it, as you can see how dirty this ring is, and it actually did not have an electrical contact with the capacitor, which is very interesting, since these two metal objects were in contact but electrically completely isolated. So yeah, that wouldn't be of some importance, because I would replace this capacitor completely, but it's an interesting thing to see what can happen to components when they're affected by some fluid, acid, that is basically in this electrolytic capacitor or whatever they're using for this electrolyte as a fluid inside. And I also use this chance to measure the inductance of this coil in pi filter. It was a little bit tricky to get the right value, but as you can see, when you follow the dip here, it's somewhere around here. Yeah, and that's very close to 1.5, and we multiply that by 10, because we're at 10 millihenries here, so that is approximately 15 millihenries. So a nice opportunity to measure it, because I don't have that value here on the schematic, so I just wrote this down. And yeah, I will use this chance to remove this plate here, and to clean the whole part of the radio, and I already practically disassembled everything, and this capacitor is also not going to be in use. I will try to find capacitors of the exact value. You could think of, for example, to add a much greater value than this one, because it's 16 microfarads, sorry, but that's actually a pi filter, and it should be calculated with these values for some cutoff frequency. So that is the whole point of these capacitors here and the coil, to have a right cutoff frequency and to get much better DC signal at the output. So basically just cleaning it now and finding replacement capacitors. Maybe I'll leave those just for the aesthetic reasons. And yeah, that's pretty much it. After this, I think we should be able to add tubes slowly and to follow the signal from signal generator that I'll be using, and we will see how radio behaves. At this moment I have everything set for DC test. I have a rectifier tube in place, all other tubes are out at the moment, and I want to make sure that it's correctly rectifying voltage and that I have a nice DC voltage at the output. This crocodile clamp is just holding these two pieces of wire here, because later I will measure current which radio is drawing without any other tube. You will see why I want to do that, because now I have opportunity to do some measurements on quality, to say that way, of rectifying alternating current, and we'll see how that will go. But at this moment I want to just measure the voltage to see what's going on with DC part, and take a look at the schematic here. Where is that? I will measure voltage on this pin here, which goes directly to the anode of audio tube, of course through the audio transformer, and between the chases, which is this wire over here. So measuring the output of DC, my transformer is set to 240 volts, which is normal for this radio, as I did a setup on its transformer to be set for 240 volts. Turning it on, and I'll give it a little time to warm up this tube, and then I will measure the voltage at the output. What I mentioned about the current here, which radio is pulling from the rectifier when nothing else is plugged in, that is of course gonna change when all the tubes are in, but what I want to see is how good actually this pi filter is, because I did some changes. I did leave this capacitor of 1 microfarad, but I have replaced 16 microfarads capacitors with 100 microfarad capacitors, which are over here. That one that you can see here, and one is below. There it is. Why I did that change? I created a simulation on a computer to make sure that cutoff frequency is gonna be good. That means that 100 Hertz is gonna be filtered out. Why it's 100? Because this is a full wave rectifier. There are 2 diodes in, and one period of alternating current is going to be switched into positive, and instead of 50 Hertz we will get 100 Hertz pulsing current here, and that's then a bit filtered with these capacitors, but also pi filter is meant to work as frequency low band pass filter, so we will see how this will go. Okay, I think that it had enough time. You can see the filament here warmed up, and the tube is already hot. Now here we are measuring DC, at the moment set to 2000 volts, and we'll see when I touch this pin here what we have. 350 volts, we can say. Yeah, 350 volts. Okay, I will use this voltage as well for my simulation on a computer, which I will show later. And now I want to measure current, which is going at the moment here, which should be quite low, because there are no other tubes here. But yeah, we will see what that current is as well. And there it is. It's just 2.4 milliamps. Just 2.4 milliamps at the moment, which is quite normal. Probably a couple of resistors with a pretty high value are drawing this current. There is a setup, very simple. So we have 350 volts and 2.4 milliamps. Now I can calculate what is the equivalent resistance of the whole radio at the moment, and that would be, just to show you where that current is going, it's over here, so that current is measured at this point. And why I need that, it's as I said, I have a computer simulation of this pi filter, and I want to check if simulation or mathematical model is matching what I have here in practice. We don't need that at all, but it's at least to me very nice and an interesting experiment. And later, using this oscilloscope, I will check what is the AC component as a leftover from rectifying, and I can repeat the same experiment later when the whole radio is working, when every element is back in its place, and when it's amplifying some signal, so I can see how pi filter is behaving then. Because I'm doing this just because I really like this setup. I really like that pi filters, because you cannot find them. They were quite often used, but not so much. You can find newer versions of tube radios from 1960s, late 1950s, 1960s. They don't have pi filter, and there was a huge amount of hum as a leftover from rectifying, which you can clearly hear in a loudspeaker. But back then, like 5% of hum was normal. That was a standard, like a maximum that any factory would tolerate. But you can go with that, for example. But I think at the moment I am pretty much sure that this radio, although it's from 1934 or 1935, is going to behave much better, and that is why I want to check this stuff.